it's a great pleasure to welcome Juan Carrasquilla, and I'm very honored that he decided to cross the Atlantic to spend a few days here in Paris. Juan has been a pioneer in this field of using neural networks, not only in machine learning, not only for the parameterization of neural quantum states, but also for other applications, in particular applications to tomography. So last time I discussed one of his major works on this field, and the paper with Giacomo Torlai and co-workers, but also applications to quantum computing more recently and other fields. So let me tell you a few things about Juan. Juan has done his PhD at the CISA in Trieste. He worked with Sandro Sorella and especially Federico Becca. And you know, with hindsight, I realize how influential this school of the CISA has been in this field, with the much regretted Sandro and Federico Becca and Michele Fabrizio, how influential they have been in this field of variational wave functions for correlated electrons. Actually, quite several people in this room have gone through this amazing school. Juan did his PhD in 2010, I think, at the CISA, and then moved for postdoctoral positions. In particular, he was at the Perimeter Institute in Waterloo for several years. I think you are still a fellow of the Perimeter Institute. Right, yeah. And then he moved to Toronto, where he holds a position with the Vector Institute. He's also he has also a chair from the Canadian Institute for Advanced Research in the field of artificial intelligence. And I already mentioned in my first lecture how the CIFAR program was key and influential during the so-called AI winter, in particular, in sustaining that field. So it's a great pleasure to have Juan today, and the floor is yours.
Yeah, okay, thank you so much for the introduction and for the invitation. I'm really excited to be here. So I'm going to tell you about neural networks and representation of quantum states and tomography. So I'm going to basically present two examples of representing quantum states with machine learning. And they come from, or were inspired through computer vision and natural language processing. And it's kind of like my personal journey through discovery through this field and so on, and how I approached it. And so hopefully you'll see my point of view about this. So first, let me give you the example related to computer vision. And I'll start with this example. It's the handwritten digit classification. It's one of the prototypical examples in computer vision, where the task is to take an image of a digit, a 0, a 1, a 2, and so on. And the task is to have an algorithm read the image and spit out the number it represents. Okay? And so the computer vision community has developed a wide array of powerful supervised learning algorithms based on neural networks. In particular, this is one based on a feed-forward neural network, such as the ones you've explored in the course. And yeah, what this does is to read this set of pixels, and then it spits out a number that the computer understands. And the first thing I thought at the time, this was 2015, already a few years ago, was that, so I started learning machine learning, and so I thought, okay, this can be understood as a perfect 5 plus fluctuations given by how we write digits, or how humans write digits. And so that was kind of like the motivation for us, and then we started thinking, can we use these techniques to classify phases or snapshots of a phase of matter. And so if you can imagine that if you can classify these digits correctly, as we do nowadays with these algorithms, you can easily classify, say, a ferromagnetic phase compared to a high temperature phase. So this is just an image of, say, black pixels with plus some fluctuations versus a high temperature phase, which is random fluctuations. So I'm sure you believe now that this machine learning algorithm will have an easy time recognizing these phases, and so that was the idea we first explored at the time in this paper, which was very fun for me, and it changed my career and so on. So it was a lot of fun, and kind of like my first paper on using machine learning for physics. In the same paper, we studied a different system, not just the Ising Hamiltonian. We studied this Wagner's Ising gauge theory. Is a bit of a more interesting Hamiltonian. It's classical. It's given by this Hamiltonian. It's defined on the square lattice, and this Ising variables are on the squares. Sorry, on the bonds of the square lattice. Okay, and the Hamiltonian is basically a product. So sum over the plaquettes of the lattice of the products over the 4 spins on the plaquette. Okay, and it's well studied, it's well understood, and the ground state is a highly degenerate manifold with short-range spin correlations. So these ground states form a soup of strings of aligned spins. Okay, they look something like this, and when you go into the quantum regime, they become this string net condensates. But we're going to look at the classical system. Okay, and so so the task that we came up with was, can a neural network discover or identify or classify zero temperature ground states of this classical Hamiltonian versus infinite temperature states. Okay, and so this is how they look. Okay, so one of these two is a ground state, and the other one is a high temperature state. And as you see, it's just much harder for those algorithms, or at least for humans, to recognize the two, or to understand the difference between the two. Okay. So it turns out that if you apply the same type of neural networks, so fully connected, feed-forward neural networks, it's just really hard, and you can't distinguish these images or this configurations using this algorithm. So basically what you do is you train, but then when you test the algorithm, it just has a 50% accuracy, meaning that it's basically randomly guessing what is the ground state versus which one is the high temperature configuration. Okay, so that was very interesting. We were confused, and but then we figured out that we were missing something. We were missing that we can use the locality of the interactions in this Hamiltonian, and we then took inspiration from computer vision. So we use a convolutional neural network with local filters, so 2x2 filters that we use 64 per sublattice, lattice with 2 spins per unit cell, and then we just come up with simple architecture based on convolutional neural networks with some nonlinearities called ReLU, and with this we were able to then classify this training or this task perfectly, or 99% accuracy, using this convolutional neural network. And so we were very excited at the time. And so what is a convolutional neural network? So this CNNs use a mathematical operation called the convolution to process the information in this data that have this natural grid-like topology, like a 2-dimensional lattice. And so it has a trainable set of parameters that people call the trainable kernel. And for each layer Q, you have a set of output channels or images, input channels, and you have a shift, okay, M along the Y direction and along the X direction. And so what you do basically is you take this kernel, which is basically a set of little matrices, and you slide them around and you multiply the original input times this, and you create basically a set of new images that you're processing with these filters or with these kernels, and they become your trainable parameters. Okay, and then after you've done that operation, you apply a nonlinearity again, and that gives you a new say a new layer. Okay, and that I represent here with this colorful images. and you do this on, and you make this architecture very deep, and then they work really well for computer vision and for this type of tasks. Okay, so this is my new, like my processed image. These are the kernels, and this is the input image, or the features in the previous layer of the convolutional layer. And I represent here just the input. So that's the zeroth input. Okay, so that's roughly how they work, and so on. And so we were excited, but we wanted to understand why this worked. Okay, why was it was being able to classify this spin configurations. And so the picture that we draw was that for a CNN, it basically you go and look and distinguish and uses these filters in the convolutional neural network to detect satisfied local constraints. Okay, of like induced by this Hamiltonian. So this Hamiltonian, basically you have a minus here, and so you want this products over the 4 spins to be positive so that you minimize the energy. And so basically what this convolutional neural network does is it just goes and checks for these products on each of the plaquettes of the lattice. And so that's how we understood eventually what this neural network was doing. And the connection with computer vision, the way we see it is, so in the filters of convolutional neural network trained on computer vision tasks like digits and images. So these filters, these kernels get trained, and they look like this. They're basically detecting edges in the images. Okay, and they're very similar to the so-called Gabor filters that are used for image processing and so on. And so this the equivalent of this thing that happens in computer vision, and is also believed to happen in our visual cortex, in the way our brain works and perceives, is as this, right? Like it's just that you come with these filters and then you check for satisfied plaquettes. Okay, so you say do a product over spins here, and this one is satisfied, whereas this one, for instance, this 4 spins break the energetic constraints imposed by the lattice. Okay, so that's what it does, and what this neural network that we trained did, and it's basically looking or seeing this constraints, or these monopoles, if you want, in the theory, or these broken strings in the gauge theory. So then what we did was we came up with an analytical model for this neural network, which is basically encoding that information in the filters of the neural network. So we took a look, and so you have 4 spins per plaquette, so you have 2 to the 4 different configurations, and so you need 16 filters to analyze each of the different configurations. So we have the 16 filters, and then we slide them around the image, and trying to detect these monopoles or these broken strings, and then we have a fully connected layer that counts how many you have. Okay, and that was the trick that leads to 100% accuracy on this sets. And yeah, so that was the model. So, and if you want, this cold neuron, the neuron that detects cold or ground state configurations, behaves like this, right? Like this is like the Boltzmann weight of the Hamiltonian, and at 0 temperature, basically, this becomes 1 or a positive number. If you have all the configurations satisfied, or 0 if you have 1 where this product is -1, and so you get 0. Okay, so that's the behavior of this, what we call the cold neuron, the neuron detecting the cold configurations. And okay, so that was very fun, and this is these are the details. So these are the filters, the way we construct them, and so on. It's not important. It's just to show you. And this is the weights of the final layer that counts these configurations. So basically, the convolutional net layer encodes the knowledge about the Hamiltonian of the system. Okay, so that's the conclusion. But then what's the connection to quantum states, right? Like that's where we kind of like conclude in our paper in this paper. What is the connection to quantum states? And then there's this the famous Hamiltonian, there's the toric code Hamiltonian. So it has this part, which is the classical part that I was explaining before, but then it has also a term that induces dynamics or quantum fluctuation and is defined on the vertices of the lattice. Okay, it's a product over the stars of the lattice and a product of a sigma x. And this induces fluctuations. And so then we took inspiration from this paper. It's a paper based on PEPs, as a tensor network representation of the ground state of this Hamiltonian. And what they have is that they have this Boltzmann weight that we were using as our call neuron. So we had this call neuron here. It's exactly the same as what they do in the PEPs representation. And what they do is they then make a coherent superposition of this Boltzmann weight at 0 temperature. Okay, so then we took that. We said, okay, so if the PEPs construction uses this, we can also use it because we have a representation of the call neuron that behaves the same way as this Boltzmann factor. And so what we did is, yes, we took our convolutional neural network, we got rid of the warm neuron, the neuron classifying the high temperature states, and we just stripped that out, and then we're able to prove that the ground state of the toric code Hamiltonian can be written down in terms of a convolutional neural network exactly. Okay. Then after that, so we wrote our paper, and then people started playing with the same type of ideas, but using the restricted Boltzmann machines and so on, and they were able to write those ground states again. They're very simple, but in my opinion, non-trivial. But the whole thing became like very nice because now you can represent this ground state of the toric code using CNNs, RVMs. More recently, we were able to do it with recurrent neural networks and so on. So it's all like it all makes sense. So this was the first kind of like my first encounter with the idea of a neural network quantum state in the context of this ground state of the toric code, through the lens of thinking about computer vision and classification of this snapshots that you see in a Monte Carlo simulation. Okay, so that's the first example. So the second example comes from natural language processing. It's a bit more recent and more fun, in my opinion. So natural language processing is this branch of computer science, linguistics, and machine learning concerned with giving computers the ability to process text and words in a similar way humans do. Okay, and it's used in machine translation. When you go on Google Translate, you're using natural language processing based on neural networks. It's used in speech recognition when you use your phone and Siri and so on. Sentiment analysis, summarization of text and text to image and more. So it's very powerful, and it's all over the news right now with the advent of ChatGPT, which many of you have seen. So ChatGPT is a machine learning model which interacts with humans in a conversational way. So you can has a dialogue format that makes it possible for those models, ChatGPT, to answer follow-up questions and admit mistakes and challenge incorrect premises and so on. And it was all over, even today, it's all over the news, and it's a lot of fun to play with. So last night I was thinking, and I've asked this question before, so is Mona Lisa smiling? And that's the ChatGPT's take. So it doesn't say yes or no, right? Like it's basically, it's been a subject of much discussion and interpretation over the years. And basically what ChatGPT says is that it's seen as somewhat ambiguous, with a touch of sadness or even a hint of irony, and that the interpretation is subjective and open to personal perception. So that was the answer last night. But then a few months before, I had asked ChatGPT to draw Mona Lisa using ASCII art. Okay, And so it came up with this a few months ago, but these models keep being trained, and so this one was last night. Okay, so it's pretty bad, but it at least tells you it's smiling, right? Like but anyway, ChatGPT can be great at creating dialogue, but it's terrible at drawing. Okay, so yeah, it's very impressive, anyways, but and fun to play with. But anyway, so how do these models work? That's more seriously. So these models are based on neural networks, okay? And neural networks are powerful universal function approximators that can, in principle, represent any function if you give it enough parameters. And in particular, in natural language processing, they model objects that look like this. So it's conditional distributions or probability distribution. For instance, probability distribution of an output text conditioned on an input text. So this is what ChatGPT and all these related models do. When you do a translation, what you do is you're modeling conditional distribution of, say, a text in English given a sentence in Spanish. When you do language modeling, you do probability of language or of a sentence in a language and so on and so forth. And you just plug them in a neural network, and then they spit some probabilistic output, which is a translation or an output consistent with a question that you asked, and so on. So these models usually have this structure, right? Like, so they have an encoder. And so for instance, you ask ChatGPT, write a poem about quantum states, and you encode it, and you create a high-dimensional representation, a vector in high dimensions of this sentence or this question that you've asked. And then you feed that vector to a decoder, and that represents this probability of the output. And so this is the conditional part, and this is the probabilistic part. And then you decode the probability distribution, and then it produces a sentence that's consistent, hopefully, with what you wanted, what you wrote. And so in a world of quantum states where entanglement dictates, and so on, and so forth, you can imagine writing a whole poem about it. And there are many examples, so we'll discuss this one in detail, recurrent neural networks. So it has an encoder, and this high-dimensional representation of what you encoded, say ABC, gets encoded into H0, and then a decoder that produces the probabilistic output. Okay. But then there's also transformers, which are those more powerful models that are used in ChatGPT and so on, but they follow the similar structure, right? Like they have an encoder, high-dimensional vector, and a decoder that understands it and produces an output. So how do we use these models to represent physical states? That's what we've been thinking about. And so first thing we do is we get rid of the encoder. There's usually no encoder, although I've seen applications of people representing quantum states conditioned on something, for instance, on parameters in the Hamiltonian and so on. But typically, in the examples that I'm going to discuss, I just get rid of the encoder, and I set this vector to 0. Okay. And then what we do, so usually a decoder outputs words, right? Like in a world of quantum states and so on and so forth. So we're going to replace these characters or these words with degrees of freedom of the system in some computational basis. For instance, spins or measurement outcomes in some computational basis. Okay, and so we go from a dictionary of words, so word 1, word 2, through word n if you have a word-based model, and now we'll replace that with a spin up or spin down if you're using spins. Okay, so that's what we do in terms of replacing the degrees of freedom of the model. But then this part, so we'll have a decoder that represents a probability distribution, and probabilistic models for language are usually based on autoregressive models. So this term autoregressive originates from time series models, where observations from previous time steps are used to predict the value at the, say, current time step. Okay, and so basically we consider a distribution over n variables, sigma 1, sigma 2 through sigma n, and what we do is we apply the chain rule to write it down. So this can be done pretty generically. So this is basically, this joint probability can be written down as a product of conditionals. So probability of sigma 1 times probability of sigma 2 conditioned on sigma 1, sigma 3 conditioned on 1 and 2, and so on and so forth. And so this autoregressive, say, term comes from this, right? Like previous observations, sigma 1 and sigma 2 are used to predict the probability of sigma 3, okay? So that's how these models operate. But in general, so to specify P in a tabular form, for instance, or through the conditionals, this requires exponential resources, because you have to tabulate all these probabilities, and so that becomes quickly intractable. But then what they do in machine learning is they alleviate this exponential issue, and what they do is they parameterize the conditionals. Okay, so then instead of tabulating all these probabilities, you parameterize them through a function with parameters theta, in this case, a neural network. And then by doing that, you effectively reduce this exponential complexity, and you obviously restrict the families of probability distributions you can represent. But nevertheless, I mean, they're as powerful as what you've seen. You see ChatGPT and so on, they work amazingly. And so you don't need all this generality to produce useful results. So it's like a useful idea. And this idea then can be extended to quantum states as well. Okay, so what are the advantages, in my opinion, of using these autoregressive models? And they're tractability advantages. So computing the probability of a single configuration is efficient given some configuration sigma, because you have all these conditionals, and so you need to compute all the conditionals for a string configuration. And since you've parameterized them intelligently, hopefully, then computing this is efficient in linear time in the size of the system n. Okay, they can be sampled exactly efficiently also in linear time, as long as the number of parameters is constant or doesn't scale with the size of the system. They can be easily defined in any spatial dimension, like in 1D, 2D, 3D, and there's no tractability issues with those computations in the first 2 points. So they can still be sampled efficiently, and they can compute. You can compute the amplitude of the distribution of the wave function, and you can compare that with, for instance, PEPS, which is this two-dimensional tensor network for which even computing the amplitude or the probability of the configuration is very hard. It's Sharpie hard. That's a computational complexity. So it's, in some sense, they're more efficient than traditional high-dimensional tensor networks. Their expressive power can be systematically improved. They're easy to encode product states and mean field theory, so we can bake information about the systems that we have. We can also impose symmetries and conservation laws, and so all these advantages remain true for models of the quantum state in any dimension, basically. So those are the advantages and why we like them. And the one example that we've explored the most is the recurrent neural network, which is an architecture that dominated natural language processing until 2017, when they introduced transformers. So this is what we started exploring before the transformers became so interesting and powerful. But then let me tell you a little bit about the RNN. So it's basically the key building block of the RNN is a recurrent cell that I represent here in green. And it basically takes, it's a nonlinear function that takes input a hidden vector from a previous time step, spin configuration or the variable sigma, and you have parameters, a matrix W and a vector or bias B, and then basically you apply a nonlinearity, and with that you compute the new or the updated hidden vector h at step n. And because of this recursive structure, this allows you to parameterize the conditionals in the distribution very easily. Because if you take and you apply, for instance, the so-called softmax on this vector, so on this vector h, so this first of all represents a probability distribution because it's normalized, but also has the right conditional structure. So this becomes a function of the all the variables that you have previously seen because of the recursive nature of this function, and also becomes a normalized distribution because of the way we compute the way we renormalize, the way we normalize this softmax activation function. And so basically our parametrization of the conditionals happens through this recurrent cell, okay, with parameters W, bias vector B, matrix U, and bias vector C, okay.
I have a question here. So here you use softmax for the output layer.
That's right.
But for the inner layers you use a different nonlinear function.
That's right.
So or lieu or whatever.
It's usually a tan H for the simplest vanilla neural network or vanilla recurrent neural network. But then there's a lot of flexibility about how you choose this one. You can choose, and there are many, many different choices, and we've explored many. And but yeah, so it's basically a nonlinear function acting on the previous vector and the spin configuration at that step. Okay. So sampling, okay, computing this is efficient. You compute in linear time in the size of the system, and the sampling is basically through calling this function repeatedly. So you call it with 0 at the beginning. We initialize this at 0 and this at 0. Then you compute the probability of 1, and that gives you two numbers. Say, for instance, for spin up and down, you sample this using your favorite random function in Python or whatever language you use. And then you take this configuration that you get out of the sampling procedure, you bring it here, and you compute probability of sigma 2, condition on 1. You sample it, you bring it, you recompute, sample, recompute. So it takes linear time in the system to get a sample. And the good or the important thing about this is that the samples are independent of each other, so you don't have to use Markov chains to get samples out of this distribution. So the sampling is very efficient. The key insight is, yes, this model is very easy to sample, even if it encodes some complicated landscapes. Its samples are always good. It doesn't get stuck. So that's the architecture, and let me give you the example.
One last question. So,
yep.
How are the W's and H and so on optimized?
Right. So, of course, so we've defined a probability distribution. We can also define a wave function by basically adding a phase, and then the training procedures that we use depend on the task that we want to solve, right? So if you're using this for instance, for variational Monte Carlo, then you use gradient descent techniques and using computing the gradients as usual, as you've explored in the course. If you're doing tomography, then you use some sort of maximum likelihood estimation of given, say, the data set that you collected out of your quantum experiment, what's the most likely quantum state that corresponds to your data under the model, and that's how you do it. So you use some sort of maximum likelihood and gradient descent techniques on this likelihood function. So I'm going to explain this a little bit more detail in the example. Okay, so let me go ahead with the example. It's going to be tomography. Okay, the main example that I'll have here. So so it's quantum state tomography. So what is quantum state tomography? You've seen a little bit in the course already, or a significant part of a lecture. So it's basically the process of reconstructing a quantum state by measurements on the system. And it is the gold standard for verification and benchmarking of quantum devices and quantum states. It's useful for characterizing optical signals, diagnosing and detecting errors in state preparation, for instance, in states produced by quantum computers in a reliable way, for entanglement verification and more. So it's a good primitive in experimental quantum information. So quantum state tomography has been around for a while, for more than, well, as long as quantum states exist, but has been studied very carefully since, I think, 20 years ago. And they started understanding how to do it for 1 and 2 and a few qubits. Okay, and so that's well understood, and it works very well with theoretical guarantees and so on. But then why do we want to do this with neural networks, right? Like, or with any other techniques? And it's the need to go beyond the standard quantum state tomography, because progress in controlling large quantum systems. So I have examples here: trapped ions, superconducting qubit quantum computers, quantum annealers, and cold atoms. So these devices and these experiments are growing beyond the capabilities of standard quantum state tomography, okay? Because of the size and because of the availability of arbitrary measurements performed with high accuracy on these systems. So then, if you wanted to estimate the quantum states, then there's a bottleneck limiting this progress. It is the curse of dimensionality, the fact that the state space where this quantum states live is exponentially large. And so traditionally, quantum state tomography scales exponentially, so then how can we perform reconstructions of large quantum systems? So that's the motivation. And so here I have examples of some of these experiments, so they're relatively recent. So 256 atom of quantum simulator. This one is around the same size as based on the Rydberg atoms. So this is one from when I was working at D-Wave, so 1,800 qubits, quantum chemistry, and so on. So lots of very large quantum experiments for which we could potentially be performing quantum state tomography with the measurements that they produce in the lab. Okay. So then the question is how to make quantum state tomography efficient, right? Like to go beyond this exponential bottleneck in the representation and of the state of the system. So then you have to give up on the generality of full quantum state tomography and introduce some parameterization of the state, which has some sort of good scaling and non-trivial structure. Okay, so then, for instance, people have utilized matrix product states as a tensor network technique and matrix product operators in this very beautiful papers, and they work really well. Typically, this one works for pure states in one dimension, and this one for mixed states also in one dimension based on matrix product operators. And so they work really well, but best suited to one-dimensional systems because of the limitations of tensor networks to one-dimensional systems, in particular the MPS and the MPO tomography. So that was nice. And so our first attempt at using neural networks, which was discussed in the course already, was this. So we introduced a parameterization of the quantum state with good scaling based on restricted Boltzmann machines for pure states in this paper where I participated. And then later on, Giacomo Torlai and Roger Melko, they developed a method or an architecture to perform quantum state tomography on mixed states on this paper in the same year. So this one, so they were interesting. So we were able to capture pure states with structure, the structure captured by the restricted Boltzmann machine. We found high fidelity, good scaling. We were able to reach relatively big system sizes. but the states were limited to pure states. And then Giacomo and Roger went ahead and they studied mixed states with structure given by the restricted machine, but they had poor scaling in the sense that they needed to use data set, and then the post-processing of the data would lead to a bad scaling. Okay, so that was an interesting development, but it had a limitation of the post-processing of the data so that you could train these models to represent the quantum state. So, so then the question that I asked and that we solved in this paper was, can we can we target mixed states with some structure and have good scaling also for mixed states? Yeah.
Sorry, do you understand why or what could be the cause of this bad scaling?
Yeah, the intuition is so you have to take measurements in different bases. And then when you rotate those, you incur in an exponential cost. And when you rotate this basis to the computational basis where you're writing the density matrix. And what I understood is that you cannot choose only a few bases to do the reconstruction. You need all the information about the states to be able to fit the model in high fidelity. So it turns out that for pure state, we were able to design a set of special bases whose number is only a polynomial of the size of the system, such that we were able to have high fidelity. Okay, and that's something that's not understood. So we don't know why we can do that, but we did, and it works really well. Even though the set of measurements that we took is not informationally complete in principle, we were able to reconstruct many different types of states with that set of restricted bases. Whereas in this case, in the paper, they explained that they can't do that. Or I don't know if they write it in the paper, but they told me or something. Okay. And it has bad scaling. They need to use an exponential amount of bases to do the reconstruction with high fidelity. Is that a reasonable answer? Okay. Okay. So then the second question I asked was, can we do mixed states with structure given by whatever architecture I use with good scaling? Okay. So, so the approach I took was we will parameterize the measurement statistics of an informationally complete measurement, and we use recurrent neural networks and transformers to do it. Okay, so we demonstrated the idea first numerically, and then we did a small experiment. Okay, so let me show you how. So, sorry, what time is it? Oh. Okay, should be finishing soon.
No, but you have 20 minutes.
Okay, okay, good. So yeah, so learning quantum states with recurrent neural networks. So how do people reconstruct states? So you prepare the unknown quantum state in the lab. You apply a measurement that probes enough information about the quantum state because you measure and you collapse the state. You have to prepare the state and repeat on and on. So as you do that, what you're doing effectively is you're collecting a data set of measurement outcomes, okay? And so what you can do with that is, in the spirit of machine learning, infer a reconstruction of the quantum state that's consistent with this data set, okay? And at the end, you certify the reconstruction. For instance, you know what the state you wanted to prepare, and then you go ahead and compute, say, the fidelity or a metric that compares the reconstructed state with the state you meant to prepare in the lab, for instance. And so hopefully that tells you, yes, your experiment is doing what it should or not. And so we took a set of measurements that are called informationally complete, and they're based on a positive operator value measures. They're a set of operators, M, A. They're positive semi-definite, and they sum up to the identity. Okay, so they describe the experimental apparatus that you use to measure the state. There's a connection between quantum theory and experiment through the so-called Born rule that connects the theoretical description of your state with the apparatus in the lab, which is represented by these measurements, and then what you see in the experiment is the outcomes A in the lab, and they come with certain probability P, and that P is basically the trace of the state times the measurement that you used. Okay, so we use so-called informationally complete measurements, which basically mean the following. So the measurement statistics P of A contains all the information about the quantum state, okay? Which, if you want, is like you have a state, and it's a three-dimensional object, for instance, and for you to be able to reconstruct it, you should be able to see it from many different angles, okay? And so you need a bunch of operators for you to be able to reconstruct the state, to see it from many different directions. So that's the first meaning. The other meaning that the information completeness has is that the relation between rho and P can be inverted. So here we go from rho to P. So you can do this, for instance, with, say, measurements in the computational basis. There's a probability distribution associated with measuring in the computational basis. But usually you lose the information about the phases and about the full structure of the state rho. But if the set of measurements is informationally complete, this relationship can be inverted. You can write rho in terms of P. Okay? And so that's the type of informationally complete measurements that we take. And the other thing that we do is we do tensor products of single qubit measurements, because motivated by the fact that these are the ones that are easily available in the real experiments in quantum computers and in cold atoms and so on. And so you go ahead and you invert this equation because this measurement is informationally complete. And this is the expression. It's basically the probability distribution contracted with the measurements and a matrix that depends on the measurements that you used. And it's basically a way of factorizing the quantum state in terms of single qubit operators and this probability distribution. Okay, so we factorize the state in this form, and all entanglement and potential complexity of the state comes from the structure of this probability distribution at this point. And this expression allows you to do everything basically in this language. So you can do tomography, you can do like real-time dynamics, for instance, in terms of probability distributions. You can do open quantum systems, measurements. You can do everything else just using probability, okay? Because of this connection to the quantum state. So we've derived, for instance, Schrödinger equation for P and so on, and we can do dynamics. We've done a lot of work using this idea, okay? Okay, so then the insight was this, right? Like, so we will parameterize the statistics of the measurement, and then we'll invert this expression. We'll invert this probability distribution using this expression, okay? So basically what we do is we have this model, so we have this probability distribution, we learn it with a recurrent neural network or with a transformer. And the data comes from seeing the experiment, right? Like, and so we use to learn it, so we've collected these data sets, and then to learn the model, we basically use maximum likelihood estimation to infer the parameters of the model given this data set. Okay, so when we've done that, then we can invert this relation and construct an approximation of the quantum state.
So Juan, in practice, the size of your TA prime matrix is what?
So this one is it's a matrix. It's a very large matrix. It's 4 to the n by 4 to the n. So that's right, but it has a very special structure. So because of, okay, so the measurement operators look like this. Let's say in tensor network notation. So these are the physical indices. This is the outcome, say. This is sigma, sigma prime. So this is what M looks like, okay? But then we do tensor products of this as our measurement operator, okay? And then the definition of M is this, right? Like, so it's trace of M and MA. A prime, okay? So this is our TAA prime. And so this is how it looks as a tensor diagram. And so you'll take, say, M and a second M, and then trace, say, for a single qubit.
But you restrict M to have a specific bond dimension.
Yeah, so it has a bond dimension 2, okay? But then what we do is we have tensor products of M's. So then T has also a tensor product structure, right? Like, so T basically looks like this. So where this are these two indices, okay? And then when you do inverse, so inverse of tensor product is tensor product of inverses, right? So we don't have to say -1. So we never have to, exactly, we never built it. We only built the one for a single qubit. We invert it in the computer, and then we patch. And that's how we make the whole thing efficient. That's also one of the reasons why we choose that our measurements are tensor product, so that we can analytically use this expression. Yes?
When you say, so how many data you have typically? So what's the number or the order of magnitude? Is it a lot, like in machine learning application, or is it more?
Yeah, it depends on the state that you're trying to learn. Typically, like, for instance, if we have a state with, I guess I remember the maximum I had was, say, 100 qubits, but for a very simple state like the cat state. So all up plus all down, and we wanted to learn that. We use about, if I remember correctly, 10 to the 5 samples from the distribution. So not too bad. Okay, so let me go through the examples. So, which is precisely this, and hopefully I'll be able to see some numbers, but I don't remember if I have them. So this GHZ state, or the cat state, is basically all spins up or 0 and all spins down. And as a density matrix, it looks like this. It can be represented as a tensor network, and a matrix product state with bond dimension 2. So a very simple state. We also apply local depolarization to the state so that the state becomes mixed. And local depolarization is a model of the coherence of a qubit, where with probability 1 minus p, each qubit remains intact. So this is, again, this pure state. And with probability p, you apply a Pauli matrix, okay? And that becomes then a mixed state. And it turns out that we can also represent this as an MPO, as a matrix product operator. And so, again, it has a very simple form. And then, so we tried learning it with 2 qubits, right? So locally, like a 2 qubit with local depolarization using a restricted Boltzmann machine. So what we found is that it works really well. Okay, so this is the KL divergence between the GH state probability distribution at the outcome of the measurement versus our model. And as we train the model, then the scale divergence goes to 0 very quickly. And then as a function of p, then the noise applied, what we found is that it's easier to learn this as at high noise. Okay, and it's basically because at high noise, this probability distribution approaches the uniform distribution, which is always easier to learn than zero noise one, which has more like structure. Okay, that's what we found. This is a very simple restricted Boltzmann machine with 4 hidden neurons and 2 visible ones. And this is the fidelity between, so the classical fidelity is this so-called Bhattacharya coefficient between or overlap between the 2 distributions, and it goes to 1 quickly as well as we train the model. And finally, the quantum fidelity, which is this object here, and it also goes to 1 quickly. So the problem so this is only 2 qubits, so this is reachable with exact tomography and so on, but then when we tried to scale to large systems, then we found that it was difficult to scale. Okay, so then we switched to RNNs, and so with the RBM, so we were able to go to 5 qubits at most. But then when we went with the RNN, with this architecture that I explained earlier, we were able to go to up to 80 qubits, and we were able to reach high classical fidelity, 0.99 and so on. And so what we found is we perform a size scaling analysis for how many samples we needed. And what we found is that for learning this particular state, this GSZ state, we needed a linear number of samples to reach a fixed classical fidelity. And the numbers at the largest system sizes were about 10 to the 5 or 10 to the 6 samples at this system size, so it's not too bad. So I guess a key aspect about this model is that it can represent high-dimensional distributions very compactly, and it has a similar behavior to a matrix product state. It has that tensor product behavior, right? Like, because you're multiplying these conditionals and you're passing information through a vector, which behaves similarly to the bond dimension. And indeed, Filippo has a paper about connecting matrix product states to recurrent neural networks, which is very nice, and the connection is very, very clear in their paper. And so indeed, yeah, the behavior is very similar to a matrix product state, especially if we linearize the model, and that matches the structure of the GHZ state, which is a matrix product state. There's also this paper where they also establish some connection between MPSs and RNNs. So we went ahead and learned ground states of local Hamiltonians from data. So these are 2 examples. So the first one is the transit field Ising Hamiltonian in 1D with 50 spins. What we see here is the correlations, the expectation value of the sigma x operator across the lattice is computed with DMRG. And these are our reconstructions in green, which match well. So as you see, so this is 50 spins, and we are able to compute correlations, even though all these matrices would be difficult to invert. So we bypass all that because we have some control over this. And these are the spin correlations along the Z direction, and they match really well with the DMRG simulations. So this is for the Heisenberg model in 2D on a triangular lattice. And these are the spin-spin correlation functions of like out of DMRG, and these are the spin-spin correlations that we computed out of the reconstructions that we performed on the data that we collected. So finally, we performed an experimental demonstration using one of these IBM machines that are available online. And we constructed, again, a GHZ state, CAT state with only 3 qubits. We couldn't get a lot of data out of IBM directly, so we went ahead and we used what we could from the machines online. And so these are the reconstructions from traditional quantum state tomography, and these are our reconstructions. So these are a representation of the density matrix in the computational basis. And they match really well. and they both have high fidelity with respect to what we thought we should get, and the only difference with respect to what we've done before is for this paper we used the transformer architecture. And so yeah, we were happy about it, and so with this, let me just conclude and discuss a few extensions before flashing the conclusion. So we've introduced this probabilistic simulation of, probabilistic representation of the quantum state using recurrent neural networks. But then, as I said, we can do all sorts of things with this, right? Like we can track the dynamics of the system if we want. We can study open quantum system dynamics. So we've worked on this. So we've done, for instance, a probabilistic simulation of actual quantum circuits using transformers, which is described in this paper. More recently, we did quantum process tomography, and it was recently published. We did open quantum system dynamics using transformers and in this probabilistic language, which is similar to this paper, and so on. So seems useful, at least it was fun for us and useful. So to conclude, so we've introduced two examples of applications of machine learning ideas in quantum systems. Basically, the ground state of the toric code written as a convolutional neural network, and from like thinking about computer vision at the time, and so that was my first like personal journey into this idea of quantum states through machine learning. Then reconstructing quantum states with RNNs, and as you've seen and throughout the course and hopefully the lectures and the seminars, so there's a lot of work, and I hope all this showcases the opportunities that machine learning techniques, ideas, even the research culture can spark in the field of quantum physics. I think it's a privileged time for quantum research. Lots of opportunities from arising from artificial intelligence, ideas in quantum computing, which are, I think, today's most promising computational paradigms that, I mean, we're all excited about and happy to explore. And this cross-fertilization between condensed matter physics, quantum information, and artificial intelligence is exciting. It's growing steadily, so hopefully we will come up with some fun problems and solutions in the near future. And yeah, with that, I'd like to thank you all for the attention.